All right, so I'm going to switch back as you're maybe working through these and go back to my slideshow here. I just want to call out these different parameters that we're playing with. So I'll back up one here and just reiterate that hopefully in your first investigations where you changed the time of year and the year block, you found some pixels where you can characterize change with the gray measured values in the background. What we're doing now is trying to get the algorithm to actually capture the change that we think we see with our eyes. And again, I mentioned earlier, you might know about a place based on spatial context. The algorithm is only working with whatever values it gives, we give it, and in this case, it's just a single pixel. So if the numbers you're giving it have no awareness of context, then it won't have any awareness of context, but you can certainly use that just as you're trying to train and learn about the parameters that work, the time of year that works, and the parameters. So this is the part we're on. Can we get the algorithm to find the change we're interested in? And this is a figure from just the original paper. And this describes in excruciating detail, if you want, how these different pieces work. And so you'll see these green boxes sort of connect to the process, and some of them actually relate to the parameters. Like there's a despiking parameter. There's an option for finding more vertices. The way the algorithm works is it overfinds vertices and then calls them back using two different strategies. So that's one of the parameters as well. And then there's a parameter for how to pick the best model based on the p-value of the F statistic. You can dig into all this more if you want, but this is just to draw your attention that if you really want to play around with the parameters and know what they mean, this is where you look. So what we're hoping is that you now have identified, at least for a couple places with change, some vertices solved from segmentation. Now we get to do the fun stuff, although I think it's fun to just look at the time series in pixels myself, but a lot of you are probably interested in making maps. So in other words, running the algorithm across lots of pixels, not just one at a time. And the way that this works is we have to think about what's happening on the per pixel level, but then apply that across all the pixels. And so we think for a second about the time series at a pixel level. And so we're going to look at a chart here. This should be a familiar looking chart now. The gray values are the original measured values. The red one is what I came up with from fitting the algorithm in a particular case. Those red lines are bounded by vertices that have a number, two numbers. One is the year, one is the Y value of the spectral index, right? And so if we just compress our entire time series down to a list of these vertices, you can almost think of that as a database, right? It's just a list of numbers, and you can query the different segments based on those numbers to find stuff you're interested in. So in this case, if we characterize and sort of describe what these changes are to allow us to pick the stuff we're interested in, this index, NBR, has a high value for vegetation and a low value if there's no vegetation. So this first segment, the red line, is drifting downwards from the beginning of the time series all the way through to about 1991. The red line is just a straight line going down, and that suggests a progressive loss of vegetation. That's what it suggests. Now, is it always that case? Perhaps not. And ultimately, any of these things that we map, we have to validate or at least try to understand. You can see that this second, there's a little teeny segment where the angle has changed just a little bit. I would call that a poor fit by the algorithm. It's going in the right direction, but it would suggest that something interesting has happened in 1991 and 1992. Not sure that that's really the case. Then we have a period where it's relatively flat, and that would suggest that the vegetation is kind of just hanging out, doing its vegetation stuff. You could convince yourself maybe that it's increasing a little, but the gray line doesn't really suggest that. This is a pretty flat line, pretty stable. And then boom, we've got a precipitous drop, an abrupt drop, a loss in 1 year. And that's some kind of probably disturbance. And then finally, we've got a post-disturbance vegetation response that happens with the segment after it. And so I'm talking about each of these segments, kind of describing the character. interpreting them relative to the magnitude and the timing of the change, right? If I know that a decrease means a loss of vegetation and it's happening slowly, then it's some kind of chronic loss of vegetation. If it's abrupt, it's probably a fire or a clearing. And if it's going up, it's some kind of growth. Those are very broad brush descriptors. And so we can, if we think about what we do after we do the segmentation, we can say, well, let's just look through our database of all the, for every pixel, let's just go through each one and say, do we have a very short, abrupt, short time period loss based on the direction of the change of a certain magnitude? It has to be greater than just a little teeny blip in our time series that we can find. Are there any segments that meet those criteria? So again, we're post-processing what comes out of Landtrender to say, let's find segments of a certain character. And then once we have those, then we can identify based on the vertex X value, the year that it happened. And so in the case of an abrupt loss, the year that it happened would be the first year after the drop happens. And that is, in this case, because it's just a 1 year segment, it happens to be the vertex of the endpoint. But we can identify that year. And so what we can do in this interface, and then also in a scripting format, if you want to dig into that later, is you can run the Landtrender temporal segmentation algorithm and then subsequently query the results that come back from that and say, find me things of a certain type and map them out. And so in our interface, we'll do that in a second, but here we can say, I'm interested in disturbances that only happen in a given time period that are relatively short, say less than 4 years, so 1, 2, or 3 years in duration, that have a magnitude greater than such and such, then in the index that I'm using, in this case, I'll say 100 scaled NBR units. And this is what we'll get. This is a sort of precursor. Let me stop sharing here and go back to our interface. Do this. Okay. So let's say I believe that I've found a set of parameters that are okay. And I've confirmed that some places that I've looked at, the change is both captured in the Landsat record and then the algorithm appropriately finds it. And then we've got a bunch of different things which I'm going to skip. We've done the pixel time series, right? We don't need to do that right now. I'm going to go to something called change filter options. So again, we're filtering through our database to look for changes of a specific type. And a bunch of different approaches here. So I'm going to look for loss, but you could also look for gain, right? So if you're interested in what happens after a disturbance, let's say, you might change this to gain. If you're interested in the type of vegetation change, we have a bunch of different options here: fastest, slowest, oldest, newest, greatest. I'm just going to look for the greatest, which just means of all the segments that might be going down in my time series, I'm going to look for the biggest one. And this really speaks to one of the challenges of working with time series data like this, is that, you know, plenty of us, or certainly over the case of 30 or 40 years, will have landscapes where there are multiple changes, multiple disturbances. The algorithm, the temporal segmentation algorithms can find those. How you then query the database to parse them out, you know, determines a lot of what your map looks like. So if you pick the greatest, you might actually be interested in the most recent. Then you might have to change that to the newest, for example, but we'll stick with the greatest for now. Filter by year. So again, this is not the year that the temporal segmentation is happening. This is saying, once you've done that, what years are you interested in? I'm going to actually just pick 2000 to 2020, let's say. I'm going to filter by magnitude. So I'm as I said, I'm working with NBR, and this is where I'm going back to the Landtrender options. The source index here, NBR, is where I select that. So you can sort of play around with that if you want to use a different index, but I'm going to use NBR. It worked fine. And so I'm going to use the magnitude of 100 scaled units as my threshold. My operator is greater than, although we give you both. So this means that it's going to go through all the segments. It's going to find ones that are dropping because I've said loss. It's going to, if there are multiple ones, it's going to say, well, just give me the biggest one. If there are any that happened before 2000 or after 2020, it's going to ignore those. It's going to ignore any that are not greater than 100 scaled units. I'm going to make it so that it is a relatively abrupt disturbance. So this is filtering by duration of less than 3 years. And then this last one speaks to the sort of patchiness of disturbance. And when we talk about MMU, filter by MMU, that's the minimum mapping unit. And so we can actually run this, all these filters come up with maps of pixels that meet the criteria that we've listed above. And then after we've done that, we can look for whether that pixel is just out by itself, alone in a sea of no change, or if it's next to other pixels that are also experiencing change. If you're interested in patchy disturbance, which most of us are, pixels are usually not super relevant, you might want to use this filter. So this filters it to 11 adjacent pixels. Anything smaller than that will not get mapped. And I'm going to say add filter disturbance imagery. Now this will take a while. And I'm going to zoom in again as it's running, but it's going to take a while because it's submitting all those pixels to Earth Engine. And if you look up here in the top in your layers, you can see that it's got little progress bars for all the different pieces, year of detection, magnitude, and duration. And so it's slowly doing all those. And we're going to pause here for a second. Jeff, you want to pause it and we can let folks do this? Okay, well, there's one key piece, which I neglected to say that we have to do before we hit go. If you hit go, it's going to run it for a place in Oregon. We actually need to do one extra piece here, which is open the RGB change options dialog. And this is on the control panel on the left. And this is another, I find, very useful tool. I'm not going to go into it because it requires a lot of color interpretation, which would have a much deeper conversation than we have time for right here. We do talk about this in some of our materials on our GitHub site. The key thing here, though, is that in the middle of this RGB change option dropdown is a latitude and longitude value. And what we want to do is we want to click somewhere on the map to set that value. So if I click somewhere on the map, you'll notice that the latitude and longitude numbers update. That becomes the center point of the subsequent map products, including our change detection map that we just built the filters for. So the other thing that I want to do is make this buffer something that's kind of small so that it doesn't take a lot of time. I'm going to change this to 5 kilometers. It defaults to 50. And once you set those, that's all you need to do is just open this dialog, click so that those latitude and longitude point to your part of the world, collapse that again, go back to your change filter options, add the filter disturbance imagery, and it will do that centered on the pixel area that you picked with the buffer of the area around it. So as this is loading, and hopefully as you're maybe getting a chance to play around with this, just want to speak to a few things. So again, we have different layers that are showing up here: duration, magnitude, year of detection. The color schemes for these are sort of buried in the scripts. But if you want to query any of these things, just like in a lot of the Earth Engine apps, which you may end up using, and certainly just in Earth Engine in general, this is just a reminder that if you go to the upper right of your Earth Engine window, there's the inspector tab right next to the console tab, right? So if you really want to know what the specific value of a given pixel is, you can click on the inspector, and then if you click somewhere in the image, it should give you an update of what is actually under that pixel. And you're getting lots and lots of information here, of course. But in this case, for example, it's showing us the year of detection is 2004, the magnitude is such and such, the duration is such and such. So if you want to understand what these values are, you can use the inspector to do that. And now for my little area, which is only 5 kilometers centered on that point I picked, Here's my map. What do these different things mean? I'm going to turn off the year of detection and the magnitude and the duration. Okay, so here's our landscape. And what we've done is we've asked the algorithm, we've asked this interface to run the LandTrender algorithm, do the temporal segmentation using the recipe that I picked in the LandTrender options, so that it built the image collections, conducted a compositing process, so we get one number per year, calculated a spectral index, in this case NBR, passed that to the algorithm, which then used all those parameters to run gazillions of computations out on the cloud in Google World. It returns just the vertices. That's the end of the LandTrender piece of this, again, as I say. And then we then use the change filter options to take those vertices at each pixel, query, look for the greatest loss that occurred within a certain time period, that has a magnitude greater than such and such and a duration less than such and such, et cetera, filtered to a relatively large patch size, and report out for every pixel that meets those criteria, report out some stuff. And so the stuff it reports out is the year of detection, the magnitude of the change as defined by us in the change filter, and the duration. And so I'm going to turn on the year of detection here. And what this shows, if I go back to my inspector, if I wanted to do that, I can click in the green area and it will show me, and I'm scrolling in the upper right here. Let's see here. 2004 with a magnitude of 875. So this was a fire that happened between 2003 and 2004. And so the first year it was registered in the Landsat archive was 2004. If we turn that off and just turn on the magnitude, the colors here represent a scaled version of the magnitude of change in NBR units. And you can see that in the center of this fire, for example, the magnitude was relatively high. This is a sort of a green to red color scheme, which I recognize is maybe not the best for color blindness, but you can change these ultimately if you want to do this in your own scripting. And then the last one is duration. And in this case, the duration for all of these are fairly short. I'm going to go to a different place here. Let's see here. So this is Mount Hood, and I'm going to go back over to my RGB change area. And I'm going to, let's see where I want to go. I want to go roughly here. Let's see if this works. So now I've updated my latitude and longitude. I'm going to make this a little bit bigger. I'm going to make it a 10-kilometer buffer. And I'm going to change my filters to duration, and I'm going to say, instead of quick stuff, I only want stuff that's longer than 3 years. So I'm changing the filter by duration. I'm going to turn off my minimum mapping unit filter. I'm going to change my magnitude filter. I'm going to turn that off, because what I'm interested in is the maximum time period of interest, and I'm looking for loss, but I'm going to look for the slowest loss, and by that I mean the one with the greatest duration. So I'm just changing the post-processing here. I'm going to add this filtered imagery, and while this loads, we'll pause this and I'll come back and talk about it when it's done. Hopefully those of you who are doing this live, we can pause and talk about that.